So, so as you know, so I posted the first lab assignment for this course, right? So actually, so I designed this lab assignment for teaching about some how to use HDL, okay, audio description language. Actually, in this course, we will learn about the system value. So system value is a very popular HDL. So and then so like the normal programming languages, so we can use HDL for designing digital system. Okay. So actually, in the previous class, we learned about some basic concept and then some and then so actually I introduced about the some basic concept of the hardware description languages, right? And then so you know and then through this lab, then you can practice. You can practice how to use hardware description languages like system Verilog. And then so actually for this lab, so you need to use the Ubuntu, so that is the kind of Linux distribution, and then also you can use Mac OS. Okay, so which means that actually, so in order to use in order to write the code using C or C++, we need to install compiler, right? And then so the system value is the same. So actually, in order to use a system value, then we require a compiler. So actually, in order to simulate, so you also need the compiler for system value. And then for this course, we will use the equals value. So it is the value compiler, some kind of value compiler, and then it's open source software. Okay, it's free, right? So, but you need to install. You need to install this equals value on your machine. Okay. And then actually, in order to use this equals value, then we require, as I mentioned, the Linux operating system or Mac operating system, Mac OS. So if you are using MacBook, then it's okay. So you can also install this equals value on your machine. But if you are using a Windows, the Windows operating system, then I just add this link. So actually, you need to install WSL, the Windows subsystem for Linux, or you need to install VirtualBox. So VirtualBox is the virtual machine, and then on this virtual machine, you can install other types of operating system, right? So on this VirtualBox, then you can install Ubuntu. So this is the Linux operating system. But I recommend the first approach, which means that you can install WSL on your Windows 11, then Windows 10 operating system. Okay. So in this course, I will not explain. So I believe some of you are not familiar with the Linux operating system, right? This is so actually on Linux operating system, we use command line interface. So I believe the most of you are familiar with the graphical user interface, like GUI. But actually, for programming, then you need to get familiar with the CLI, the command line interface. Okay. Also, so you also, as a computer engineering student, I recommend you. I recommend you to practice how to use Linux operating system actually. So you need to get familiar with the command line interface or the Linux commands because actually for the other courses you will also use a Linux operating system. So actually so uh, so it's true that we can easily use our computers using the GUI. Also, recently we use some smartphones, and then smartphone actually provides the touch screen, and then also so it means that we can touch icons, or we can just use our fingers to use our smartphone, right? But actually, as a programmer, actually, so you know, so in this course, okay, so we will learn how to program, so how to use hardware description languages. So you need to get familiar with this environment, like Linux operating system and then CLI. But unfortunately, I will not teach how to use Linux. Okay, so we don't have enough time. Actually, this is the out of interest in this course. Okay. So if you are not familiar with Linux, how to use Linux or the command line interface of a Mac operating system, then you need to learn. You need to study by yourself. Okay. Okay. There are many articles, and then also you can find the useful information in the internet, right? So you can use Google. So Google is your best friend. Okay. So you can Google some topics. Then you can also search for how to use the Linux. And then also you need to actually you can learn how to use Linux commands in CLI, the command line interface. So I will not teach about the Linux. Also, actually, but if you are not familiar with the Linux operating system, then you can get help from TAs, teaching assistants. Okay, so also you can post your question on the not Blackboard. You can post your question on Piazza, right? Then TAs will answer your question. Also, TAs will help you, right? Okay, so also so you can just click on this link for installing the Linux operating system or VirtualBox on your Windows machine. But on your Mac operating system, you don't need to install any Linux operating system for this course. Okay, this is because you can install eCars Bello very easily on the Mac operating system. Also, once you install the Linux operating system, you can also easily install eCars Verilog. And then also we require a GTK wave. So this is the waveform viewer. Okay. And then so we require eCars Verilog. It's called iVerilog in the Linux operating system. But so iVerilog is the compiler. So compiler for system Verilog or Verilog and HDL. So eCars Verilog is the open source HDL compiler. Okay. And then actually for simulation, we need to check the waveform. So where's the waveform? Okay. So you can find the example of waveform here. Okay, so you can find the time axis under this horizontal axis. Also, you can find the signal names on the vertical pane. Then you can also find how the signals change by time, right? So this is the waveform. But so in order to check, check the waveform, then we also require the waveform viewer. Okay, and then so we will use the GTK wave. So this is the also open source waveform viewer on for Linux or Mac operating system. So you can easily install these tools on your Linux operating system using the apt get install command of the Linux operating system. And then if you're using Mac operating system, then actually, so in order to install the eCars value, then you firstly need to install brew. So this is the kind of app management tool for Mac operating system. Application management tool. It's an app management tool for Mac operating system. So firstly, so if you do not install, so you do not install the brew on your Mac operating system, you need to firstly install brew. Okay, so just click this link for installing brew. Okay, and then once you install the brew, then you can also easily install the COSE value, like using the brew install command, right? Brew install command, and also brew install command. You can also install GTK wave. Okay, and that's it. So, and then if you are using a newer version, then also you can install the Python. Okay. So this is the instructions for Mac operating system, and then this is instructions for Windows operating system. Okay, so this is Windows, and this is for Mac operating system. Okay, so and then this is the Hello World module. Okay, so I also showed this module in the previous class, right? So as we learned in the previous class, so in order to make a module, okay, so actually when you write a code using system Verilog, then this Verilog file needs to include one module and list. So single system Verilog file can include multiple modules, okay? But at least a single system Verilog file needs to include one module, okay? So this is the example of file, system Verilog file. So this is the hello world module, okay? So this is the module start with the system Verilog syntax module, and then it ends with end module, right? Okay. And then this is the module name, okay? And then just type the these lines, okay? So actually, so I believe you are familiar with the GUI, the graphical user interface. And then in order to make a text file on Windows, then you can use a Notepad app. Okay, but actually, so as I mentioned, so in order to use this eCars value, then actually you need to use the command line interface of Ubuntu or Mac operating system. So actually, so you need to also use the command line text editor like PI, or Nano or Emacs. Okay, so I recommend to use Nano. Okay, so you can, I believe you can easily learn how to use Nano. So which means also you can easily install this Nano text editor using sudo apt get install Nano on the Linux operating system. So if you're using Mac operating system, then you can also use the basic text editor, no Mac operating system. Okay. So right, make this module. So you can read the instructions here and then make hello.sv. This is file. So like you can make a file like the nano hello.sv. Okay. So and then type this line and then store this file. Okay. Then file will be generated, and then after you created the this hello world, the hello.sv file, then you need to compile your module using equals Verilog. So this is iVerilog. So this is the command for equals Verilog, and then this is an option. Okay. And then so this is the source file hello.sv. And then also you can find the -o hello. So this means that the output file name, the compiled out file name is specified by hello. Okay. So after you execute this command, then hello will be created. So this is the binary file. So which means that you can execute this binary file. Okay. But this is the compiled HDL file. So which means that actually you need to use the application like BBP. Okay. So if you just execute the BBP and hello, okay, then you can observe the displayed hello world. Okay. Hello world will be displayed on your screen. Okay. So this is the very basic, very first system variable module you can make. Okay. Understand? So the problem is that then I believe some of you are familiar with the Linux operating system or CLI, but some of you are not familiar with this Linux operating system. Sometimes you can think that, oh, this is not easy. This is not easy to use the Linux operating system. But as a computer engineering student, then you need to get familiar with Linux operating system. Well, also the command line interface of Mac operating system, right? So if we are not familiar with these command line interfaces, then try to learn and try to learn by yourself. Then try to search how to use Linux or how to use some command line interfaces or commands of Mac operating system using Google. Okay. Okay. Also, you can get help. So you can contact TAs, and then you can email TAs, and then you can get help from TAs. Okay. You can make an appointment for the to stop by TA's office. So you can get sorry you can get help from TAs. So try to use Piazza. Okay, so this is very important. Okay, the second mode you need to make is to imp and gate. So actually, I also showed this module in the previous class, right? So as you can see, the module starts with the module, and then it ends with end module, and then end two is the module name. And then as I mentioned, A, B, C are input and output port, right? And then A, B are declared as input ports, and then C is declared as an output port, right? And then C is A and B. Also, you can find the system Verilog operators here and here. So in this course, we learned about the basic logic gates, right? And then using system Verilog, then we can implement. So we can implement we can design the behavioral model, behavioral model of the this our design, our system. This is the system. So system Verilog supports the operators for describing the behavior of basic logic gates. Okay, so we learned several basic logic gates: AND gate, OR gate, exclusive OR gate, also NOT, and then NOR, exclusive NOR, right? So you can find the equivalent system value operators here. Okay. So AND is AND, so OR is this one, and then exclusive OR is this. Okay. So you can find some examples here. Okay. So in this example, so this is the two input AND gate. So I use the AND operator, right? So this is the some basic module that you need to make, you need to create. And then actually, then so you make a module, and then you want to check this module is correct or not, right? So after you write the code, then you need to debug your code, right? Because every code includes bugs or errors. So even though you pass even though the compiler does not report any errors or syntax errors, but your design, your code will include bugs, right? So actually, it's not possible. Actually, it's not possible to make the correct code for the first try at the first try, right? So every code will include bugs or errors, right? Then we need to verify our code. Then how? In a computer, in the programming language, so if you use programming languages, then you can just print out some variable, the value of some variables, right? Using print command or print function. Actually, print is a function, right? But so in the system variable, so we can also use the similar command like the print command or a display command. But usually, this is the hardware description language. So actually, we can check the real behavior using waveform. So that's why we need to install waveform viewer GTK wave. But in order to check the behavior of our design, we first need to create test bench. Okay, so this is the test bench. So okay, so let's go back to the slide. So in the previous class, we learned how to design a module. Okay, you can create a module using module syntax of system Verilog. So you can declare a module, then you can specify a module name, and then you can describe the behavior or structural models of your module, right? So you can make a module. Then also you need to verify your design. Then I mentioned that you can verify your design using a waveform, right? So waveform means that so you can just provide the input, and then these input values are changed by time, and then based on the some different input values, then you can check the output value. Then if the output value is equivalent to the some desired output value, so it's the expected output value, and you can think that, oh, my design is correct, right? But in order to generate a waveform, then firstly we need to make a test bench. Okay, so this is a test bench. Okay, a test bench is also module. So it's also kind of module, but this module is designed for simulating your design. Okay, so this is also module, but this module is the test bench module is designed for simulating, so verifying your target module or your target design. Okay, so maybe even though you are familiar with some kinds of programming languages, but you are not familiar with this verification model, because so you need to remember that audio description languages are designed for implementing real hardware, right? So it means that we can verify our design like the real behavior of our real hardware, right? And then as I mentioned, so we live in real world, and the hardware works in the real world, and then which means that that real world includes time, right? So time passed, and then the values are changed by time. So we need to emulate. We need to simulate this real world behavior of our design, right? So test bench is also designed like this. So this is the test bench module, right? So test bench, and then this is your module. So this is the module designed by you. Okay, this is the target module, and then in the test bench, you need to generate the input values. So these input values can be changed by time. So this is called the input stimulus. Okay, so this is the input values programmed by you. Okay, so inside of the test bench, then input values are generated, but these input values are changed by time. So input value is given. So it's a programmed input values are given to so this is target module. Then, so if the input is given, then our system will generate output values, output data, right? So this is the output signal. Then we can just monitor the values of these output signals in the test bench. Then we can check the output values are correct or not, right? This is the test bench concept in the system variable. Okay. So it looks like this. So this is so it's called the DUT. So DUT means the design under test. Okay, so using a test bench module, we test our target module. Okay, and then in order to verify our target module, firstly we define input values changed by time, and then we check the output values created by this DUT, design on the test module. And then if the output value is equivalent to the expected value, right? Then we can think that, oh, my design is correct. But if this output value is not equivalent to the expected output value, then you can think, oh, our design is incorrect. So the module is designed incorrectly. Then we need to fix our design. Okay, that's how we verify our design, and we just debug our design using Testbench. So this is the same code. So in the lab, in the first lab, so actually, so this is the end-to module, and then also this is the same module. So this is the design of the test. So we can make this module, and then we can define the output value by input signals, right? So this is the DUT. And then actually, in order to verify, in order to check the waveform by this end-to module, we need to make a test bench module. Okay, so if you read the this lab document, then also you can find that this is the test bench module. Then you need to also create this test bench module. Okay, this is another file. So you need to make the TB. TB represent the test bench. Okay, so actually you can use any names for your test bench module, but in order to distinguish this test bench module with some other normal modules, that usually we add TB on the back as a prefix of the module name. So we can find that, oh, this end-to module is the name of the file name of this end-to module is the end2.sv, right? So this is the system Verilog module for end2. Also, you can find that the file name of this test bench is the tb underbar end2. So in represent, this is the test bench file of the end2. Okay, so usually we add tb for specifying test bench file, test bench module. Okay. So, okay, let's go back to the slide. So this is the example. So actually, I also provide the test bench module and then for you. So this is the example. So also the test bench module need to start with the module. Okay, so as I mentioned, this is a module, right? So it's a normal module. So actually, in order to make a module in system Verilog, then we need to declare the module and then using the module name. The module name is the tb underbar end2. So it also ends with the end module. Okay. But you will think, oh, what is this? What is this line? So if you compare this Testbench module with the design, so your design module, then you can observe that, oh, our design. So normal design module starts with the module, right? Firstly, but what is this? In the Testbench module, so actually I added this line, so called time scale. Okay. So this is the kind of the primitive. So that is the some special command for system value. So which means that we just configure the some the time unit for our simulation. So you need to remember that we are learning about how to design hardware, and then I mentioned that in the real world, hardware works in the real world, and then which means that we need to consider time. So this is the major difference of the hardware description language. So in the normal program languages, we don't need to consider what the time. So actually every lines are executed sequentially, but we do not consider the time in our normal programming languages. But hardware description languages are designed for implementing real hardware. So which means that actually we need to emulate the behavior of real hardware. So which means that we need to emulate the hardware behavior by time. Okay? You understand? So actually the time scale declares the basic unit of time. So which means it declare the basic time unit is the 1 nanosecond. Okay, so you can find some number here, right? Actually, in the Testbench, this represents the delay. Okay, so I just use a number to represent a delay, but it because we specify time scale of this testbench, this module as the 1 nanosecond. So this delay represents the 10 nanosecond. Okay, so time scale just specify the unit of time. Okay, so actually we need to declare delay in the input stimulus, because as I mentioned, the input values are changed by time. Okay, so this is time scale. We just define the time unit of this test bench. Okay, okay. And then this test bench, this is test bench name. Also, we can find that this module does not have any input and output ports. Why? So it is because so if you see this slide, then you can find that this is the Testbench module. Okay, so you can find the big rectangle, the big box here. So this is the Testbench module. But you can also observe that for this Testbench module, this module does not include any input and output ports. Right. So normal module like this module includes input ports and output ports, right? Right. This is system. So the system receives input and then a system generates output signals, right? But this is normal module. But in the testbench module does not include any input and output module. Okay. Instead, the input signals input stimulus are generated inside of a test bench module. Okay, we just define the generated inputs. Do you understand? So test bench module does not include any input and output, but we just generate the input stimulus, input values inside of the test bench module. Okay. Also, the output signals is tested. Output signal is monitored inside of the test bench module. So that's why the test bench does not include any input and output signals, input and output ports. So no input, no outputs, but I just declare internal variables. Okay. So this is a logic type. So and then I declare three internal variables A, B, and C. Right? So it looks like this. So this is the TB underbar and the module. Okay, and then I will test the and two module. Okay, so and the module includes the input and output port, right? Input port is the A, B, and then output port is the C. So we already know that C equal A and B, right? So this is the DUT, the design of the test. Okay? So inside of the test bench, like a TB underbar and two, we declare the internal node A and B, and then we can define the values of A and B inside of the test bench. But these values are changed by time. You understand? So we declare the A, B, then C variable here, and then we connect these variables to the input and output port of the DUT, design of the test. Okay? Then we just change the A and B, and then we will check the output signals C. Then how can you change these input signals? So you can find the initial statement here. So we will learn about the initial statement later, but initial means that, this block will be executed when the simulation starts. So which means that this initial block, the initial statement, will be executed at the very first time of the simulation, so initially. So that's why this is called the initial. So at the start of the simulation, this initial statement will be executed. So if we use this Testbench file, it starts with the initial statement. Then so this is some specific commands for generating waveform. Okay. So actually, the Ecars Verilog, so we can generate the waveform using BCD format. Okay, this is the BCD format. So this is some specific commands. So you can just understand that using the dump file. The dump file just specify the file name of the dump waveform, and then dump bars to specify the variables. The variables checked by this dump waveform. Okay, so this is the special command for the Ecars value. Okay, okay, and also you can find the A equals 0 and B equals 0 here. Okay, so I mentioned that in the Testbench module, we need to generate input signals. Okay, so A, B is connected to the input and output ports of the DUT, so and to module. Okay, then we need to generate input signals. So this is input. These generated input signals are called input stimulus, right? So initially it is 0, A, B. So initially it's a 0 nanosecond. At the time it is 0. Okay. And then you can find the top 10, right? And then this represents the delay, as I mentioned, the delay. So then it means that after 10 nanosecond, because the time scale is the 1 nanosecond, after 10 nanosecond, A becomes 0, B becomes 0. So actually, it's the same, right? So this is the 10 nanosecond. A is still 0, B is still 0, right? And then also after 10 nanosecond, okay, another 10 nanosecond delay. It's the 10 nanosecond. So this is the 20 nanosecond from this time scale. So A is still 0, right? And then B is 1. So it changes to 1. Okay? Then another 10 nanosecond. 40 nanosecond. A becomes 1. B is 0. Right? So these lines describe the input values. But as I mentioned, so we just control the input values, and then we can just change input values by time delays. Okay. So this is so after 10 nanoseconds, just 40 nanoseconds, then input is also changed. Okay, do you understand? So these input values are given to DUT. Then C will be also generated. So, this is the combinational logic. So input is given and output signals will be generated by input values only, right? So if this, then we can check the value of C in the waveform, right? So if you use GTK wave, then you can check the waveform of the ABC. Okay. So after 10 nanoseconds, it will be finished. It finishes simulation. Okay. So this is the example of test bench. But you need to remember that. So enough to verify. So enough to check the correctness of our design. So this is called the design under test. Then we need to also implement Testbench module. And then Testbench module includes the input signals changed by time. Okay, so input signals are given to our design on the task, then output signals will be generated, right? Then we can check the output signal values. Okay, if these values are not equivalent to the expected value, so we can define some correct values, correct outputs by input values, right? And if the output values are incorrect, then we need to fix our design. Okay, that's the verification flow. So, and then in order to verify our design, we require test bench. Also, so you can find the last line here. So it represents. So you can find N2 DUP ABC. So actually, this is the folder is on Ciation. So actually, our test bench need to include. So this is called the instance. So our test bench needs to include the design of the test inside of the test bench file. So which means that this module, our end module need to be included inside of the testbench file. So then this instantiated module, for this instantiated module, we need to connect the input and output ports. Okay, so do you understand? So this is the module name to be instantiated, and then this is the instance name. So I just named this instance as the DUT, the design on the test, and then this is the module name. So it means that I just include the end to module using the instance name of DUT. Okay. Then also you can find these variables are connected to the input and output ports of the module. So if you see this end to module has the 3 ports, A, B, C, right? So and then actually this A, B, C is the internal variable of the test bench, and then A, B, C is mapped to the input and output ports of the end module. Okay, so which means, this is the A. A is connected to the input port of the end module. B, the internal variable of B is connected to this port B, the second port of the end port B, and then C is just the output, and then we need to connect also C to the internal variable of the test bench, because we need to check the output value inside of the test bench. So C is also connected to this C. So finally, we need to instance the design of the test, our design inside of the test bench file, right? So it may be tricky because the verification process, the verification flow of the HDL is a little bit different from the normal programming languages. So as I mentioned, the normal programming languages, so we can use a print statement or a print function. So and then we can also check the value of the variables by using print function, right? But so in the hardware description languages, then we can just monitor the output values. So the values of these input and output ports. Also, we can check the values of internal nodes using Testbench. So for this purpose, we need to create the Testbench module. So actually, if you design your own digital design module, then you firstly need to design your own design. So it's a target design, and then you need to also implement the Testbench module. Okay, so because Testbench module is required for verifying your design. Okay, so I also provide this Testbench module. So and then as you can see, this is longer than the design of the test. So our target design, because so we need to define the changes of input signals, right? So you need to also make the different file using for this Testbench module. Okay, so this is the tb_end2.sb. Then also you need to compile your module, so your design and your Testbench module. So you can find a list of system variable files that need to be compiled, right? So this is the list of system value files to be compiled by equals value. Okay, and then this is the output. Output and equals value will generate and two. So this is the output binary file, the compiled file. Okay, this is the option. Actually, not to. So the -G 2005 dash SV is required for compiling system value. Okay. So then if we just execute this equals value command, then end2 will be generated. Okay, then you can execute this compile end2 file using bvp end2. Then what will happen? So if you want to see some detailed information for your compiled end2 file, then you can also use the -b option. -b usually represent variables. Okay, so variables. So which means that if we usually in the Linux application or Mac OS application, if we just add -b option, then it represents variables. Okay, variables. Then it will provide the additional information, so detailed information for your design. Okay. Okay. Then using the GTK wave, you can observe waveform. Okay. So if we just execute this end file using the BBP, then so actually we define the dump file. So dump file includes the waveform information. Okay. So and then this is the name of the dump file. So tb_end2.bcd. Okay. So this is the waveform format of the kind of waveform format. So you can load this waveform file using GTK wave. Then you can observe waveform. So, but in order to observe your some signals, then you need to select the signals to be observed with the GTK wave. Okay. So this is the output. So actually, the GTK wave is use the graphics user interface GUI. So it looks like so. You can find the tb_end2 here. So this is the module top module of the Testbench module, and then also you can find some signals. Okay, here ABC. You can if you just select the ABC signals inside of the GTK wave, then you can observe the waveform, right? So this is the waveform. So as I mentioned, so actually in the Testbench file, so you can find the 10 nanosecond, 20 nanosecond, 30 nanosecond here, and then you can also find that input signals are changing. So the input stimulus, input values are changed by time. And then these changes are defined inside of Testbench, right? So here. How about the C? C is the output signal. Then because the input signal values are changing, then you can also observe the output value signals generated by DUT, the design on the test. Okay, so this is the AND gate. So you can find that if the A is 1 and B is 1 here, then C becomes 1. Okay, so it's correct, right? So So this is the design process. So then so it's a little bit tricky because so actually the design verification process or design verification flow of the system value is different from the verification flow of the normal programming languages. Okay, but just if we just uh, follow these instructions in the first lab, then if you can generate some this system value modules correctly, I believe you can easily do this first lab assignment. Okay, so 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 you can test the lower two gate. Okay, so the operator is different. Okay, and then also you use the different dump file name, and then different Testbench module name. Then also you can find the door2. So the door2 is instantiated in the Testbench. What to do? So you need to create the door2.stb and then tb on the one door2, the Testbench, and then also bcd file. You need to generate the bcd file. Okay, and also you need to capture your waveform, the generated waveform by door2 gate. So tb on the one door2, and then submit the PDF file and then your source file, like the door2.sv and then tb on the one door2.sv and then tb on the one door2.bcd. So waveform file. Okay. Any questions? Okay, so if you are not familiar with the Linux environment or Mac operating system CLI, then start today. Okay. Okay. So actually, this is very simple assignment, but so I believe some of you are not familiar with the Linux or Mac operating system CLI, then you actually I believe so the instructions. So instructions in the lab document is enough, but if you're not familiar with the CLI environment, then you may believe this you may feel this is difficult. You may believe this is difficult, but you need to get familiar with these Linux or Mac operating system, right? So you are, as I mentioned, you are taking the computer engineering course, right? Okay, so I explained about this test. So on your report, you can your report can include on the actual waveform. Okay. Okay, so by doing this first lab assignment, then you can practice the verification flow. The verification flow using the HDL tool. Okay. So we use the COSE value, that is the HDL compiler. So it's a compiler for system value, and then we use GTK wave. So this is the waveform viewer. Okay. Okay. So now we will learn about we will learn about the system value, data type, and operators. Okay. So data type. So the system value handles the digital signals. So actually, the basic data type in system value is bit. So we need to represent bit values using data type. And then the basic data type for this bit data is logic. Okay, so logic. So if you see this example, okay, so you can find that, oh, we declare variables A, B, and C, and then these variables are declared as a logic type, right? So it's a different. So in C, we can use integer floating point or double precision floating point, something like that. So, but in the system below, the basic data type is logic, and then logic represents the bit values. Okay. So then bit values can be used for this logic data type. So we can use 0 and 1, obviously, because I mentioned that we use logic data type for representing bit data. And the bit data includes the 0 and 1. So we can use the 0 and 1. Also, we can use the X and Z. So what is X? X represents the sometimes done here. Okay, in the truth table, so we use X for representing don't care value, right? Also, it represents contention. So sometimes we can observe X value in the waveform, then it means that actually if we can observe X in the waveform, then it usually represents its contention. Okay, and then if the value is not initialized, so actually in the test bench you can find that I initialized the A and B, right? So at the start of the simulation, A is initialized as 0, and so B is initialized as 0. But if I do not initialize these values, actually, the initial value is X. Okay. So if you just remove this line, you can find that in the waveform you can observe X value. Okay, because the values are not initialized. So in the logic data type, X represents the don't care, okay, or uninitialized or contention, and Z. Also, we also learned about the high Z, so high impedance. So it's the same for the logic data type. Z also represent high impedance or disconnected. Okay. So actually for this logic data type, we can use 0 and 1 and X and Z, right? Also, we can represent vectors of bits. So actually using only one bit, using only single bit, we can just represent 0 and 1, right? But we actually enough to represent the very large number, right? So like very large number, then we require multiple bits, right? So these multiple bits need to be declared as a vector of bits. Okay, so we can declare a signal like the A3 down to 0. So it's actually in a hardware we frequently use the down to, not 0 to large value. So actually we just declare the vectors like using the 3 down to 0, like 3 to 1, 0. So it represents a vector of 4 bits, okay, like the A3, comma, A2, comma, A1, comma, A0. Then we can just these values like the A3 down to 0. Okay. So and then inside of the system value, its value treated as an unsigned. What does that mean? So for example, if we just use the 3 down A, 3 down to 0 equal 0 equal 1, 1, 1, 1. So then we need to use the B. So actually this represents the 15, not -1. Okay. So if we use the close complement number, we already know that if the 1, 1, 1, 1, and if this MSB is the sign B, then this is the -1. But actually inside of system value, all B factors are unsigned numbers. Okay. So actually, so 1, 1, 1, 1, it's equivalent to it's 15. Okay? Not -1. So you need to understand that inside of the system value, if we just use logic data type, then it's the unsigned value. Okay? So let's see this table. So you can find some data type of the system value here. And then actually, so you can find the value here. So actually the system value is the extended version of value, right? So a system value also includes the features of value, but it's easier, right? So actually the system value has the data types like this, okay? So you can find the leg, wire, and integer, real time, then logic, okay? So actually the logic is the, as I mentioned, is the basic data type of system value. And then actually it's enough. So it's enough for it, so we can just use the logic data type in our module. So in our design. Okay. And then as I mentioned, the logic data type can have 4 states like 0, 1, and X and Z. Okay. Now what's this? Red, wire, also you can find a bit, byte, shoot, int, blah blah blah. So actually in the value we use the red and wire data type. The value does not include the logic type, but so actually in the system value, we just use logic data type, but in the value, we need to use the red and wire data type. So I will explain, but actually the red and wire is included in the logic data type. Okay. So sometimes we need to distinguish the use of red or wire, but in the system value, we can just use the logic data. Okay. And then sometimes we can use the integer data type. So this is the integer, just the integer, like the integer of the C. And then real, so this is kind of a float or double. So you can find the equivalent data type of C. So real is the double data type. And the time is just represent the time of the module. And then real time is the real, it's a double precision time. Okay. Okay, also system value supports this data type. Also, you can find the equivalent C data type. Okay, so byte is a char, and then short integer is the integer, long is the long. Okay, but just remember that usually in order to design a hardware system, we use logic data type. So actually enough to represent numbers, then we just use this format, like n apostrophe and then some base. So this n represent the number of bits, and then b represent base. And and then value. So this is the input. So 3 apostrophe B, so it represents, oh, this is the 3-bit signal, 3-bit, so number of bits is 3-bit, and then base is the binary because it's B. Okay, and then it's the value is the 101. So 3-bit value 101. So we can just, we don't need to use this bit value, but this is the unsized. Okay. So, and then another example is the 3 apostrophe D. So this is the 3-bit value, and then the base is a decimal. So this is the trick. Okay. So if we just use the decimal base, then we can use the decimal numbers. But it stored as the 110. So in the system value, we use unsigned number. If we use the O, this is the octal number. Okay? H is the hexadecimal number. Sometimes you can use only decimal number. Okay, so if we do not specify any in numbers or base, then it represents the decimal number. Okay. Okay, so I stop here. Any question? Okay, thank you for your attention and see you in the next class. 감사합니다.